I hope you're doing well. I'm Mr. Ish. Thank you for joining me. In this video, I want to spend just a few minutes looking at double integrals volume procedure, but which would involve a disk in terms of cross-sectional slices. Looking here at y equals sine x is 0 to pi over 2 in terms of your x-axis rotating around x-axis. What is it that we're looking at? Y equals sine x would be something which would go like that, but when we're looking at from 0 to pi over 2, we're essentially cutting it over there. That's what we have, rotation around the x-axis. And now look at it. This is a region of space which would then rotate around the x-axis, and you'll have something which should look like that in terms of a solid, three-dimensional. You take a cross-sectional slice, you know it's going to be a disk having a certain radius and having an area pi r square. That's what we're looking at. How can you develop a integral? Look, the line of rotation is horizontal, so everything should eventually be with respect to dx. Equation should be y equals format, and it is sine x. You know its rotation is x-axis. You're looking up, you're developing your disks. They can integrate left and right. You can ideally just start from one point and go to the other. Integral with dy with respect to dx. Since we have a vertex here, you can start from dy integral here and then go in that direction. There's nothing wrong with you doing that. Your setup would be like this. With initial respect to dy, you have a 0 over here, and then you have this limit, which would technically, be a 1, 0 comma 1, as high as the sine x would go. But this limit is deviating along with the curve, or you can say it's traveling along with the curve by means of this effect, sine x, and dy square pi r square. Now you'll integrate it along the dx dimension. What will be your limits? 0 to pi over 2. Pi over 2. Remember, you can play around with the sides and flip things around in your mind. There's nothing wrong with doing that. Your integral here with respect to dy has a y antiderivative, sine x 0. You know this is a square and a pi. From here, what are you getting? A pi sine square x. This is going to go into your next integral. What are you going to get? You'll have a pi and then 0 to pi over 2 sine square x dx. You have to integrate this. Sine square x is a bit of a problem unless you recognize that it is a power reducing identity which can come into play. Sine square x is equal to 1 minus cosine 2x over 2. So you are essentially integrating that. We'll have here a pi 0 to pi over 2 1 minus cosine 2x over 2 dx. Separate everything along that negative sign or that minus sign. I can come over here, you've seen this. When I do it, I have a pi over 2, 0 to pi over 2 dx. That's this separation prior to that minus sign. Now pi over 2 again, 0 to pi over 2 cosine 2x dx. If you are cognizant of the fact that you have a cosine here with the u substitution coming into play, it will technically zero all of this out. Think about it. U is equal to 2x, du is equal to 2 dx, and dx is equal to du over 2. You'll have a pi over 4 develop, but look at your limits. u1 will be a 0, u2 will be a pi. The antiderivative from cosine u is a sine u. Sine of 0, sine of pi, these are all zeros. It will entirely zero out when you do your definite integral procedure. That entire part will zero out. You may not as well even look at it any further and just focus right over here. Pi over 2, and then you have an x, pi over 2, and a 0. Upper limit, lower limit, it's really just a pi over 2 times pi over 2, which is a pi square over 4. The volume generated with respect to x will be pi square over 4, and it should be right. I've shown you here everything along a horizontal line of rotation, eventually with respect to dx, as you see right here. Initially dy, then dx. Thank you for watching.